Welcome to the Girkship Corrosion channel. My name is Mariam Ehtishamzadeh. I'm a researcher in the field of corrosion and protection of materials. Chapter 3, Section 9, Types of Corrosion, Damage Mechanisms. In this video, hydrogen embrittlement is discussed, affected units or equipment, prevention, and inspection. The main reference is damage mechanisms affecting fixed equipment in the refining industry, API Recommended Practice 571. Description of damage. Hydrogen embrittlement is the loss in strength, ductility, and or fracture toughness of susceptible materials due to the penetration and diffusion of atomic hydrogen. Hydrogen embrittlement can lead to brittle cracking. It can occur during manufacturing, welding, or from services that charge hydrogen into the metal. Affected units or equipment. 1. Chromium, molybdenum reactors, drums, exchanger shells, and piping in hydroprocessing units and catalytic reforming units can be susceptible to cracking if the weld heat affected zone hardness exceeds Brinell hardness number 225. Storage spheres are often made of higher strength steels, more than 70 KSI, specified minimum tensile strength than common pressure vessel steels, and are therefore more susceptible than most other refinery equipment if not stress relieved. 3. Bolts and springs made of high-strength steel are very prone to hydrogen embrittlement cracking. Components that have a tensile strength above 150 KSI can absorb hydrogen during electroplating and crack prior to being put in service. 4. Other services where hydrogen embrittlement is a concern include where susceptible materials such as high-strength valve components, instrument components, and similar are exposed to wet H2S in FCC, hydroprocessing, amine, SW, and other H2S containing services, as well as HF in alkylation units. This figure shows internal blister caused by hydrofluoric corrosion near the top of a 1.2-inch thick carbon steel tower in an HF alkylation unit. The maximum measured dimensions of the blister were 2 feet high and 20 feet long circumferentially. For these services, equipment manufactured using hydrogen embrittlement resistant materials for the potentially susceptible components is typically selected, with the materials meeting the requirements of, for example, NACE MR 0103 or ISO 17945. 5. Carbon steels normally used for vessels, piping, and other equipment in most refining applications have low strength or hardness and are usually not susceptible to hydrogen embrittlement as long as typical welding procedures and precautions regarding controlling the moisture in welding consumables are followed. Appearance or morphology of damage. 1. Hydrogen embrittlement by itself is not visible. It only appears when cracking occurs. 2. Cracking resulting from hydrogen embrittlement can initiate subsurface, but in most cases is surface breaking. A. B. A. Cracking due to hydrogen embrittlement of a high-strength steel tube. B. Intergranular crack emanating from surface in the tube. And in these figures, A shows hydrogen embrittlement of a martensitic stainless steel pump component, and B shows high magnification fractograph of the fracture surface showing intergranular nature of the cracking. 3. Hydrogen embrittlement cracking occurs at locations of high residual or tri-axial stresses, notches, restraint, and where the hardness and microstructure are conductive, such as in weld heat-affected zones. Pipe restraints refer to devices used to stiffen piping systems and reduce vibrations by providing support and damping, typically achieved through clamp-type restraints strategically located near elbows, tees, and concentrated masses. 4. On a macro scale, there is typically little evidence of deformation. Cracking will appear to be brittle, with visible fracture surfaces having a brittle appearance. On a micro scale, the material will contain less ductile fracture surface but must often be compared to a fracture without the presence of hydrogen. 5. Under metallographic examination, cracking is typically branched. In higher strength steels, cracking is often intergranular. Figures on slide number 1160. Prevention and mitigation. 1. Depending on the source of the hydrogen, choose an alloy composition, fabrication, and heat treatment method and hardness limit suitable for the intended service. 2. Control the hardness of hardenable steels and post-weld heat treatment to reduce hardness and temper residual stresses. 3. During welding, use dry, low hydrogen electrodes and preheating methods. 4. If hydrogen diffused into the metal during welding is a concern and elevated temperatures bake out, for example 400 degrees Fahrenheit or higher, typically around 600 degrees Fahrenheit, may be required to drive the hydrogen out prior to cooling to ambient temperature. 5. If hydrogen is expected to have diffused into the metal during operation, a similar elevated temperature bake out 400 degrees Fahrenheit or higher, typically around 600 degrees Fahrenheit, may be required to drive the hydrogen out prior to welding for maintenance or repair. 6. Heavy wall equipment in hot hydrogen service typically requires controlled shutdown and startup procedures to control the pressurization sequence as a function of temperature. 7. In corrosive aqueous services, a protective lining, cladding, or weld overlay can be applied to prevent the surface hydrogen reactions. Please watch this video. Weld overlay is a type of cladding that uses welding to apply a protective layer, while cladding is a broader term that can include other processes like mechanical bonding or hot rolling in addition to welding. This video shows weld overlay. Eight. Avoid the use of cadmium or other plating on high-strength bolts. Inspection and monitoring. A. Liquid penetration testing, magnetic particle testing, or wet fluorescent magnetic particle testing can be used for surface cracking inspection. B. Angle beam, for example, shear wave ultrasonic testing, or Phased array ultrasonic testing may also be useful in finding as well as sizing hydrogen embrittlement cracks. C. Radiography testing often is not sufficiently sensitive to detect hydrogen embrittlement cracks. D. Visual testing is not reliable for finding hydrogen embrittlement cracks. E. If the source of hydrogen is a low-temperature aqueous environment, hydrogen flux can be monitored using specialized instruments. Related mechanisms, also known as underbit cracking, delayed cracking, hydrogen-assisted cracking, and hydrogen flaking, sulfide stress cracking, and hydrogen stress cracking in hydrofluoric acid are closely related forms of hydrogen embrittlement. The underbit cracking is introduced on video number E59, Chapter 3, Section 8. Challenge number 60. Thank you for your time and attention. If you like to challenge yourself, please answer these questions in the comments section. 1. Where does stress originate and how does it lead to hydrogen-induced cracking, HIC? 2. For prevention of hydrogen embrittlement, it is recommended to use dry, low hydrogen electrodes and preheating methods during welding. Describe the most common preheating method for this purpose.